So we see generic structures which are different from the previous generic structure. You have always the same channels, they are really close to each other. This you can see the white black. It is because
two layers.
Two layers on each other. One you can deactivate, probably recessed deactivate.
And sensory, I think.
Oh, there is it's probably ID or something like that, maybe. I don't know. Gate or something.
So shall I remove it
What
all
is
one
this?
and then put the just necessary one? Omics, sensor area.
Okay, that's all. Should be enough. Should be enough. Omic
Okay.
2 also, activate Omic 2.
Omic 2. Omic 2, you mean additional contact pads?
This blue, it's actually not my even colors. Everything is strange. Okay. Say that.
I can find the one which
Additional switch off.
yes. And Omic 2 you mean?
Omic 2, you did Omic 2 switch off?
Yes.
You switched off, yeah?
Yes.
And Omic, you had this Omics crap. Okay, switch off the Omics
Oh, sorry.
and switch on Omic 2.
Okay. Because it is additional contact pad there is one. Because there was some, we designed these things twice time.
Okay, then switch on Omics.
Do you remember there were three
Yeah.
masks?
Doesn't matter. Switch on this. It doesn't matter now, explanation. It's okay.
Okay.
So, you see, I don't want to remember this. It's not really part anymore. It's in the past. So, you see, you understand what is this, yeah?
Yes.
It's self-explaining. This is self-explaining.
Yes.
A bit too close, I don't know how much we have few, like maybe up to 100 of those things still, yeah, fabricated. So it can be used for everything, for cells, for gas, for antigens, for whatever sensors you need. So it's a generic structure, a bit close. Omics are, I think, on a lot of wafers, a bit cheaty. So you can nicely bond, I think, on this. But you have always to see what you can do. This,
You have to separate the omics from the contact from bonding pad.
yeah, Zelda did this already.
Yes.
She did this in the new mask.
Yes.
Yeah.
In this new mask, it is here. Here is the omic contact. Here is the contact pads. If there is an overlap, 100.
Switch on, please, all the masks.
Mhm.
Can you do it? All the masks, switch on. That's all. Thank you very much, and stay like that. It's okay.
Without numbers.
It's okay. Without number. So, let's go to here. What you see here, it's a universal kind of mask with these channels. It's a similar generic channel, a bit thicker, with a recessing part. One is here, one is here. It's just to see the effect a bit to the current. One can be a gate for another one. So you can just use this as a piezo gate for this, if you like to study this subject. The windows are the same from the area. This structure is also equipped with the platinum heaters, which Zelda nicely did. Platinum heater is really super necessary if you want to have like ultra fast humidity independent gas sensing. For some certain applications important. I don't know. Like when the low power consumption is not in the first parameter role, then you want to be not completely independent from humidity. For that, is a heater necessary. This structure, of course, the Yannick and Valit can also etch membrane. Actually, it needs to be done. And if you do a membrane from the backside, this heater becomes 1,000 times more efficient. From my experience, it can be that this heater, if you now apply a lot of, depends of course on the resistance, it can be like 300 ohm, 400 ohm. You can apply a very big voltage difference on this, and it will almost not heat. It will maybe even not boil the water. So if you put a drop, and then it will start boiling a bit, then maybe that's the highest temperature it could do, because it loses the thermal conductivity not only to the air, but also to the bulk. If the silicon is removed, the heater becomes 1,000 times more efficient. It became so efficient, you have to be careful with that, because you can, it all depends on the convection heat flows. You can apply it here voltage, and like you apply 10 volt and it's around 120 degrees, and with 11 volt it can be 1000 degrees immediately.
Ah.
So because it all depends how the flow, the heat flow works. If you suddenly overwhelm the flow away, then you accumulate so fast so much energy that like 1 volt will mean 1000 degrees higher temperature, and it will be white, and the sensor will live 5 seconds, then it will explode. So you have to be very careful when you do membrane. But normally, if you do fuel, you do like a study, and when I told to Ruben, the quick study is just when you have a normal sensor, like even without edge, and you put it on the hot plate and you measure the resistance of the heater at the different temperatures. Later, when you have a heater really and it change the resistance, you can assume this reach this temperature, because you can have, it's almost the same. There's a deviation only 5%. So if you put it on the hot plate, like that sensor, and you will start increasing like 100 degrees, 105, starting like from 50, 55, 60, 65, and you always measure the resistance. It will increase according to this equation of alpha plus T coefficient, the typical known equation. For platinum, yeah, you see what is the alpha coefficient for platinum, and you can really recalculate later from resistance the real temperature. When you will later apply huge voltage and the resistance will change, you can see that it's a self-heating, joule heating of the heater. You came to us, Steve? You came to us? Thank you very much. Please take a place.
Thank you very much.
I will adjust, you're lucky, we're just in the beginning of our lecture. So I was explaining this first, it's another mask set. I don't know, for UV also was shortly there. Yeah? So this is another mask set. Actually the previous it called SPM mask set because it has like all type of generic structures which can be useful. Especially now if the cluster will start to work, it will be very interesting to use these all structures. We even can repeat the same structures on the new wafers with better quality, yeah, because first attempt was not so nice and then it was some problems. We can even repeat with this new, maybe extended bonding pads, or just is doing, you can apply also for this all structures the same. So what you are saying, this is a generic, some of the generic structures could be used basically for the gas sensing with the heaters. So heater, normally, the idea of the heater, if the super low energy consumption, like in something nanowatt or whatever, is not so super important, for instance, heater helps you to be completely humidity free, and not independent from humidity. It means that you will sense always, and of course it's totally different mechanisms of the gas sensing. You heat the whole surface, and the just gas undergoes a bit different dynamic reaction, and you respond immediately, like in the milliseconds, and recover in the milliseconds. So it's just ideal sensor. If like the energy consumption is not like a freaky thing, but even for the heaters, you can apply this pulse-wise modulation to reduce the energy consumption to around a microwatt. So even with a heater, it can be installed in the smartphone, for example. And that's what I said. What I will quickly repeat. So you can, it's very quickly to calibrate. You put in the hot plate and you measure resistance of the heaters at different temperatures, like from 60, 65, 70, 75. Resistance will increase because it's a platinum, it has like 300 ohm beginning resistance, and then from these equations, alpha plus whatever, there, you can quickly calculate. Later, when you apply voltage difference and it will reach this resistance, you can assume this 5 plus minus 5% that it takes this temperature, which you already calibrate. And that's the only thing, when the Yannick will etch a membrane underneath, the heater will become 1,000 times more efficient. It will not have a loss. And you have to be very careful because it can be like from 10 to 11 volt, 1,000 degrees difference. Because if suddenly, so if you just, you apply like 5 volt and the heater is, let's say 120, which will be fully enough. 120 degrees is already, you evaporate all the water. And then you are completely, and the gas is very fast responses. This is a recessing part, very big, so it's very good. Slightly reversed, just to see the influence on the source and drain position to 6. And if you apply 6 volt, it could be 1,000 degrees immediately. From 5 volt 120 to the 6 volt 1,000. So because you will overcome, you will be, your energy flow inside will be bigger than you lose, and it will come to a traffic of the energy, and this will immediately explode at the temperature. So you have to be very careful a bit when you have a membrane. You will see it. Yeah. In the probe station, you can just burn one or two sensors, no problem. You actually, this is, and actually they are not dying so fast. If it starts to be white, you can just switch off and nothing will happen to the sensor, because the gun membrane can really easily withstand 1400 degrees without being damaged, and normally such temperature you will not reach, because before platinum heater will just melt. So it is, or just break. Melt not, that's why we have a platinum. Platinum is very high temperature sensor. So that's all. So this mask, it was kind of one of the first masks. It has this also structure, but we didn't use that. But it actually was used to etch mesa to silicon in this part, and you contact with gold. So mesa was this kind of narrower part, and you contact with gold, and you can contact the gun and do a gating to a channel through the piezo. But when you do a membrane, and on the membrane on the back you can do a bit of the electrode, you can do much better than this mesa. So this is kind of generic structures, and you can zoom out there, and we see how much of the structures we have on the wafer. This is, yeah, so we have few. This is all these structures. So we have, in principle, we never use them.
Okay.
So it's like above 100 probably from few wafers. So we can always use them now in the future.
I think we've tested them this week, no?
Yes. Yes, they start. They are different also with slicker, but yeah. And they are not used almost before. And if the cluster now will etch very nicely, so you can see how many sensors you have. So it's like normally, to my experience, one sensor can be forever. So if it's nicely etched, and with the heaters, we tested like in the IMAX, it was more than a year lifetime. So if really etched, okay, so without damage or that. So for the etching, Valid will use generic structure, which also we have a lot from this wafers, and then important just sell probably you need to like 2 or 3 wafers do all with generic structure. Do you have enough? Because generic structure is just like it's like a universal that you can quickly see enough. So
the black square was there on the.
this is the recessing part. So the channels are completely identical. They only symmetrically mirrored. Because this channel can be a gate for this at the same time, and it's just only to check, because it's like source drain a bit shifted, whether there is like some effects of non-linearity happening. And it can be just a gate, because this is like a strong conductivity can be a gate to the structure, and this strong conductivity can be a gate to the structure. So it's like you can gate with the neighbor channel, this channel, if you would like. Also, heater can be used as a piezo gate, so at the same time. Actually, it can be heated and used at the same time as a gate, which we never tested, but I just a bit tested in the IMAC, and supposed to be very, very interesting features which you can do. It's a lot of work, actually. Experiments, once the etching will work, it's super interesting scientific work for like a year easily. So if I will not just crazy, will like push you like a crazy, so you can work in the freedom a bit. You can zoom out. And I will be anyway in the contact, so you can always contact me. So the next structure we can zoom on this one. It's a bit bigger one. So this is like a super classical structure for dipping. Okay. We don't have a lot of them, and Selda already dived through a few of them, like here.
It's not me.
It's you damage everything. Well, it doesn't matter. We have few of those. These structures are not such a super important. Only just because we have another. This structure is just simpler to use. You put on such a PCB, and you can dip. Like you have some chemistry, because it's another generic. This is a crap. So how you just have to epoxy and all the shit. Here you just bond here, then you protect this with epoxy, and you have a completely thing which you can just simply dip in the liquid on the flexible long PCB and do some quick tests. And this is a piezo gate channel if you just would need it. This is a recessing part, and this is the U shape, very long. So, and this is the same, only the recessing is here to see what the difference would be in this case. And this is like also generic dipping structure. I didn't want to put a lot of them because they take huge surface, and we'll have few of them, maybe around 20 or something. So they are laying in the boxes. You can zoom out. Just that you know that we have. Then please, you can first zoom in on this sector. On this sector. Yeah. So, thank you. And from that sector, you can zoom maybe on this one first. Yeah.
Which one? This one?
This one, the first one, yeah. This one is completely there. Thank you very much. Thank you. Okay. So, what we have here? What we have here? Here we have very interesting structure. This is also gas sensor, mainly for gas sensing was aimed. You can see a 2-deck, not now, I will tell you when you zoom. This is the 2-deck, and this is the heater structure. And there is something special more, so you can zoom only on this small part. Thank you. So, that's all, it's enough. So you can see a 2-deck structure, and you can see a heater. But the idea here was, so if you do it, of course, from the back membrane, edge, it will be awesome. So it will be already super good. Light.
Yeah, that's really
It's too dark for Steve. So, but you can see this mask here. You can see this mask. And this mask, what is this for mask? So actually this is two rectangular. This is one here and this. And the idea was for the serial production, they will not do a membranes. It's just too complicated and whatever. You can do from top with isotropic edge, what they are doing now in the companies. And if you have this, and it's like, I think it's around like, I don't know, 20 micrometers, so I don't know, something like that.
To where?
Yeah,
Here.
just the thing. 20 micrometers. So if you will just do isotropic, so first you do an isotropic, so it goes a bit deeper, like 10 micrometers. You etch into through the algan gun in the depth, and then you switch on to isotropic edge, and it will just under edge. And because this is a gun material, algan is almost not etched in the
SF6.
in the
SF6 plus 1.
Yes. So and then you here the idea actually you have to etch to the silicon, and it's 2 micrometers. I mean there's no problem. It will you need a bit careful for resist, and it will reach silicon, and you do silicon isotropic edge afterwards, and it will. This 20 micrometers it will do in a quarter an hour, and then you will have this freestanding. It will be a bit bigger, it will be like that a bit bigger, but you don't care. And this will be freestanding bridge, which you can hit perfectly. And the structure, you don't need any Bosch, nothing, I mean, nothing. Bosch a bit like in the beginning, but it's actually not Bosch, it's just a gun. And then you have a freestanding, that's how they do it in the companies, they don't do it with a Bosch. Bosch is too complicated. For the whole wafer, it's very complicated. But this is like a freestanding thing. You need, of course, to protect it later. And then freestanding thing is just you hit only in this part, and it's only a small part which will be heated. And it can go really to super, very high temperatures, like 500 degrees in Canadian. And in 500 degrees, you can do any type of reactions. You can detect hydrogen, whatever, because if it's platinum catalyst, which is 500 degrees hot, you can. And this is very close to each other, and this is like they saw it in the nature. If it's like a few micrometers. If you do a catalytic reaction, this gun will immediately detect it. Depends on which gases, of course. And then this is one of the type of the structures. It's not easy to fabricate. Isotropic edge. Seldom will try on some sensors. We have a lot of the sensors. So you can zoom out, and then we can go to the next structure. So.
The next,
First the area, exactly this, and then we see because we have
different, yeah. I think this one different
This
from
is
one.
different, and this is also different.
Is it? Okay.
Yeah.
Let's check.
This is also different. Yeah. Okay. Yeah. So, but you can zoom really in the middle. Yeah. So this is actually different, but.
No membrane things.
No, this is no membrane, but there are also some things with a membrane, and you have such a spots. You also have this is without membrane. Here. This is without. This is with. You can zoom here. So on one thing, yeah. So yeah, completely the same idea. So this is a heater, a bit better, because you have here, normally on all the edges, there's a temperature development will be on the corners. It's normally typical. And this is the same idea. This is the kind of a big area, and this is openings, and then you etch to the silicon, and they all will spread, and this whole area will be freestanding. It's like, it's a whole area will be freestanding. And you can hit. Shut up. Yeah, so it was, yeah. So it was here, yeah. Thinking also with, and this is the recessing part, and you can have this freestanding nice area, and then it can be used even as a microphone, So if you just, you have this thing, and you speak to this, whoa, sound waves just, and actually it depends on the distance. Here, we didn't calculate it yet, but for example, for instance, some frequency will be really interested. This is really has to be calculated to a bit of sound things, but you can do a test. It's actually, this is a generic structure for tests. You can do gases, you can do pressure, you can do whatever. So it's actually a generic structure, yeah. You can zoom out a bit, and then we have, it's actually, we can zoom here, what is here, actually, yeah. And then on the part here, with here is a membrane, yeah. It's the same, but it's like double heater, and yeah, so it's also, this whole part will be suspended completely, freestanding, and then you have like two, and you can play with charges. So this is like gate 1 charge, gate 2 charge, to see how the polarization is working. You can, and this is what is very important, you can resonate this. So if you apply here AC signal, the whole membrane will be flexure or plate membrane. And if you want to detect something which is attached to the thing, through this, it will be like QCM.
Yeah, you can change the frequency.
Yes, you can change
the change of frequency.
First, exactly. You found the resonance frequency of this stuff, which you don't know, it will be kind of maybe megahertz or something. You will see. And then this is very interesting, close to a resonance, or maybe harmonica, like double frequency 4, quadruple frequency, and such things. It's like a generic structure to play with before you understand which kind of properties will be so important that you do next design only for these properties. Yeah, understood? So then we can zoom out shortly. Just this is all the same, and then you can really on this quadrant focus.
This one.
This one, yeah. Yeah. So. This is very important one. Here you could, for example, take this one first. It's kind of the simplest, I think. Yeah. Yeah, you can, yeah. So you're good. Yeah, you're good. Very good. Oh, okay. This one. Yeah, very good. So, yeah. It's okay, you don't need to zoom now. I just explain like that. You can move a bit more. Very good. So, I was very interested in RF transistors, very interested. Actually, RF transistors is another way of making a sensor which nobody before saw really made, but this is a very interesting option. And this is already a configuration. You can see here distances, exactly for so-called ground source, ground head. It's designed, it's a professional RF transistor, which normally you can see in the telecommunication or whatever. This is from the design which was agreed to be like 20 years ago. All the RF transistors, they have this configuration. And it's why you just later, when you study them, you go with the so-called VNA, which we have. We have already this device, Vector Network Analyzer, or VNA, which is only missing for this device is a probe station. Probe station needs somehow to find money to buy, because the probe station is a 50% of success. I mean, only to have device is not enough. You need to have a probe station for this special heads. And this headset is from Cascade Microtech. This is like a ground, this is source. You connect here and you connect here. And you can also connect here, but we did an extended contact for the purpose. If the Yannick was valid, and actually they need to do it, they will recess silicon underneath, it will be on the membrane. It means it will not cross-couple to a silicon. It's an ideal RF. Only here it will, but it's not really so brutal. And there is a special heads, you can buy them, you can order, Ayao has to order, unless he finds a place where you can go, where this all equipment is already installed, and you just characterize the chip. It's also possible. But normally this is a bit problematic, because this labs are only a few in Germany, I think. And you can zoom in on this structure. Yeah, very good. Just in transistor. Exactly. So say that drew now a much fancier transistor for much higher frequency. This one will probably have a frequency of around like few maybe megahertz. What is the principle? This is a transistor. So the current, this is the source, drain, or whatever, plus minus, this is a ground, flows like that in this contact. And normally, with this, you apply a voltage difference, that's why it's connected to 1. Sometimes they put metal contacts here, but in this case, it's everything from 2 there, because we want to see it as a sensor. You apply this gate voltage to this fork type of structure. This area just, you can see, actually it's a gold, goes completely to the end, it completely covers the whole. And it's applied, and it switches off the current which is flowing here. And then you measure transfer. From this, you apply the voltage difference. This is the source, this is one potential. You measure the transfer, how, to which frequency and with which voltage you can modulate this current, how fast, and it's transfer parameter. So one head is here, another head is here. And then you apply a current, and then you see how you can apply bias, whatever you want, and you see how you modulate the transistor. And normally this is such a calculated, this is a waveguides for RF, for like certain frequency, typical what you can use with standard heads. And normally if you recess here, you use working point, and probably, and the idea, it will really happen, we only want to see that the linearity still will be there. You will need smaller voltage to kill transistor, because left and right you will have this super sensitive areas, and it will, for example, the channel will be switched off instead of like -5, it will be switched off at -1. And the head has an idea, if it's calculated, if it's connected to antenna, you need less voltage to have nicer modulation. So you need energy, less consuming receiving devices for RF fields. It's kind of this. And so can be also used for the sensing, can be used for the sensing antigen antibodies on everything, because this is a RF kind of interaction. It's an impedance of the structure. It's an interaction of impedance, and we don't know how the sensors works on this. Even the gas was never studied. It can be the whole world. It's a completely new world. But the problem, it's a bit more difficult to study because you need a VNA infrastructure. But once you have it, and he already rented one, which cost almost 4,000 per month. It's like a colic one would be. But he just needs a bit more spend money for a probe station, even buy maybe used one. I checked on the internet, there are a few used for like 10,000, you can even buy. The important for this probe station is just a not normal probe station. It's really like a holder for this Cascade Microtech heads. And this holder is the most expensive. And the heads are also expensive. And they are not dropping in price because they all use like 24 karat gold and they are such a massive stuff. So, but if, I mean, in total, you can just like, let's say in total, paying like maybe 30,000, you can buy somewhere used equipment which will open the whole world. You have to understand this, and I think it will be made here. It's not a problem, I think. Just a question of time, maybe. Yeah. And you can zoom out. So this is a classical. Sender now created the transistor which has a gate which has only 300 nanometers. Yeah?
Yes.
So for high frequency, what is important? This was made. This is now, I think, is like I don't know. It's a 5 micrometers probably. The width, I think. So the wider the gate, desto shittier will be a transistor. Yeah, desto shittier will be a transistor because, yeah.
You zoom out, or you want to continue here?
I just want to tell you that the ideal transistor, the gate has to be the narrowest possible in order to have a parasitic capacitancy. Because if you have a big gate, like if I would do such a big gate, like a complete metallic thing, also would work till maybe like 100 kilohertz. And then it will just start to couple from the gate to the channel, so it will leak everything inductively, capacitively. It's called capacitive gate coupling. It's the most worst you can have with the transistor. So you don't have transistor working. You just the whole power you immediately put into the channel. That's what the Sven did with his silicon nanowire sensors. None of them was working because if you have a water as a gate, so they had silicon nanowire transistor, and they were applying potential to a water, like a high frequency, so you completely leak. So even if you even separate the channel, like there is no current flow, you still leak the whole power to the channel. So that's why the sensors will never work, and this is why the high frequency in the liquid is also not working. So it's actually, this is very difficult. High frequency is even without liquid difficult, but in liquid it's just completely difficult task. It needs to be developed properly with microfluidic. That's why the people who do this microfluidic contacts do it very properly. It's not so easy. Just you put transistor in the bulk of water and then you put the electrode and you apply 10 megahertz. Nothing will work. Nothing. This is physics. So yeah. So we have
Sorry.
here.
Yeah.
Here,
Okay.
put here. No, first here.
Here.
It's easier. Yeah, zoom like this part. So we have different. Yeah, you can.
Zoom out, you
A
want?
bit, yeah. So.
Roman, I'm sorry, I don't have my glass.
It's okay, it's okay. So a bit bigger, like that.
Okay.
A bit bigger.
Like that?
This is perfect. So you have a different types. So because we don't know what is the best for recessing, this is a recessing windows, for example. And we also have heaters in the same structure. So if you do membrane, you can heat, and transistor will become hot. And then it's actually to see how the mobility of the two deck at very high frequency at increasing temperature behaves. Maybe you see a completely new world of sensing with high frequency. So you have a lot of variations which has the same principle with a bit different. So we have a lot of such chips. So it's kind of fun to test will be, but it's a lot of work to test. And yeah, I'll just have to give you a bit of freedom, like to because it's So you cannot immediately perform like like do me like a super fancy sensor or something. It needs to be a science behind. But the structures will work all. It's just in order to important to understand how exactly. Because this working point and transistors are workable structures. It's just to know what is rents, what is the borders of functionality, because it will be so fancy. Because when you do RF, you have a phase. It's very important. Because phase is changed. Not only current, but phase is changing. And a lot of sensors are using phase changing. Phase is very important. It's like, phase is like you have the same current, but the RF energy comes, for example, delayed with a half of phase. It's a huge signal, like half of the phase. You have either full signal or no signal. And you only can check it on the phase. So phase is a signal, and phase can depend on mobility, on interactions, and everything. It will just delay attenuation. And you have an amplitude, and you have much more. So this is actually a very nice sensing world which has to be explored. And yeah, and VNA actually it's not so difficult. You can just the only thing for this needs to be a bit made a small reactor, which is not so actually so like difficult. It can be nicely coverable where the gas can go and such things. Yeah. So this is a transistor world kind of sector. We have, you can zoom out, yeah, you have some of them because we have some of the wafers.
The others are same?
This is a bit different, but the principle is completely identical. So you have sometimes multi-gate, you have normal gate. This is, you can zoom please in what it is? It's just recessing like that, so it's, yeah. You have like somewhere like multi-gate also, like a lot of gates like that. So yeah, and Senda is doing now the mask for super high, much higher frequency with only like 300 nanometers. We'll be doing it at external partners with a wafer stepper, and then maybe it's actually it's to think. I don't know. It depends how much has money. Maybe it makes sense to everything do it with a stepper, almost everything, not the half. It will be very clean.
The lithography
will be clean, good. This is of course the question to Ayao, because I think one exposure is like €1,000. I think will cost around. It's not okay. It's not expensive because you do it once and then you have a very nice structure. But if
But
for
they
example,
also deposit everything there, or only just lithography?
no, only lithography, only lithography. But it is like that. So Here can be a lot of things done, like recessing, yeah, like etching, like wash, like membranes, everything you can do here. Another very nice steps, if you want to have them super clean, you could do in this center in Denmark. I mean, by post even, yeah, because they will do it very nicely. They are very experienced. It's only about Yao how much he wants to pay, because if you do, like, for example, a few steps and whatever, it could cost. If you have a lot of wafers at the same time, it could cost maybe like 30,000 per batch, which is not like so crazy sum. I mean, and then you can become it much quicker, much cleaner, yield is much higher, and you do only steps which you want to do here. So this is according to Ayao, yeah. So Ayao has to decide. Better to say Nikhil is also going to decide, and Luke has to decide, all people has to decide. It's like that. If they have money, they decide easily. If they don't have money, then they decide not so easily. So, zoom out. Then, please, could you zoom this quadrant? Yeah. What is this? Okay, there's nothing special. A bit special. Yeah. So we have here a simpler, like a generic structure recessing with heaters. This is a membrane masses, but actually Yannick doesn't need this because he does this with a captain very nicely. So this round, it was meant if you would do like a chip wise, like 25 by 25s, if you want to do it like with a SIG mask, that we do all the chips at the same time and style. But when we already dice them, so you can do with a captain. Yannick is doing everything with a captain professionally. So what you have here, heater structure, very nice, but one thing has a gate here. Yeah, so this is to see piezo gate versus normal gate. And this is a real transistor actually, which can be heated with one heater. So you have a transistor, this is used as a normal gate, and another heater used as a heater. And you can see how the transistor starts to behave with the heating gradient. Maybe if you have like a lot of gases one after each other, you can do it with a PCS, you can detect selectively a lot of gases. Because each transistor will detect every gas at different temperature maximally maybe. So this is like a very funny experiment for selectivity with a generic structure. So to understand what is important and whatsoever. So you can zoom out. This is like just so you can go to this one. That's the next one. Exactly this one. Yeah, this. Okay. You don't see omics here. In one step,
Yeah.
one step back. Thank you very much. And then the whole chip.
Oops.
Yeah. The whole chip. The whole chip. Yeah. So thank you. Yeah. So the cross of truth. Generic structure. Recessing part. Perfect. Then we want to know what is kind of a gating capability to the structure, to the piezoelectric thing. So you have a gold gating here, they go relatively close, gold, and to that gates. And you can see applying, and this is on the membrane, Goulet. And if you can apply potential differences, one potential difference, two potential differences, plus minus, plus, minus, plus, to see what's the difference, minus, plus, and minus. So you can see really how you polarize this. One advantage. Second, if the Yannick will have electrode from the back on the membrane, and you have this, and you have this, or that, you can oscillate this also. So you can see piezoelectric. It's oscillatable. So you can see gate and oscillating. So with other words, this is an RF MEMS generic to see what is important in order to oscillate and how the gases or whatever modulate this channel. So this is like an experimental structure to see how the piezoelectric gates are working. You can just to the right go to the next one. It's actually supposed to be the same, only with heaters. Yeah. So you have these gates and you have heaters, which could be also used an electrode on the membrane, and this structure here and this structure here, and the 2-deck gate and the metal gate. And this is just interesting stuff. You can zoom out a little bit, and we can look on the next structure. They are all the same on this structure. On this. This is actually the same what you saw, only much denser. So generic structure heater, generic structure heater. Yeah, you can a bit move. You can see this. Also, some of them are with gates. Yeah. Yeah, it's just the same, completely the same, only denser, just to have it a bit more. Now with this structure, this is just structure to play. Actually, the channel is this one on the ground, and it was meant like to be with membrane because this is the point of maximum stress. So if you have normally membrane, it's always like that. So if you simulate stress, this is the bulk material, and the membrane is named here. And normally stress is like that, yeah. So it's like stress, then it's a huge difference of the stress. Then this is the biggest stress, then it's like then stress goes highest here and goes like that, and it's again a huge difference, and then it goes like that. So here it's a stress changing. So with other words, membrane is like that, yeah. So the curvature is like that. Here is one curvature, this is another curvature, here is another. Normally this radius are much smaller typically because it goes like that. This radius is very small, so that's why it's such a huge stress. So this is like, for example, like plus, minus, and this is like minus, and this is the how's the stress, yeah, plus, and this is the points of maximum stress. That's why if they have a membrane and also the silicon, they for example put piezoresistive rings here, or if you have two deck, it should go like that. This is the like kind of conductive thing, and the point of maximum stress recessing parts are just here placed. This is like the same principle. So it's a very sensitive pressure sensor, for example, or chemical sensor. So if you have this membrane, it's like a microphone, and depends how big is this membrane. This is one electrode. This is a second electrode. You apply, and the membrane oscillates like a 10 kilohertz. I don't know what the resonance frequency is. You have to see this with the VNA, and this is a recessed part, or without recessing, and everything which you can put here, functionalize or whatever, and this is like a gas sensitive part will totally be a different, so you can have a physical stress, and you can have a chemical, and everything. So this is like a very nice membrane, which is very sensitive. Here stress is huge, so once you start to etch here, you have a very strong modulation to conductivity of this. And if you oscillate, you can have even from plus and minus on the current you can influence. It's kind of it's a piezoelectric sensor.
It's again like QCM.
It's very similar like QCM. Very similar. So even without 2-deck, it's a QCM.
Yeah, exactly.
Just if you remove this, you have this electrode and this electrode, you can oscillate, you can really see very nice. I mean, you can see, if it's like room temperature, you can see how water builds up. If you increase humidity, the water layers, you will be sensitive. If you have the 2-deck parallel, which is cannot even interact with this, it doesn't necessarily interact, but it will, because this gets electric, and this is also electrons. It starts to interact, and then you can see actually this the sensor has a lot of modes. You are working with this element, is the sensitive, and 2-deck is interacting with it. And if you switch it on the current, you can see if the 2-deck will be switched off, it will interact differently. So it's like a 2-deck enhanced QCM. Or you operate vice versa, only 2-deck you read out. And with the QCM, you just interact with this, and it depends what is on this frequency will influence. So it's a lot of modes. You can play with the structure a bit and see something very interesting. We have like a few dozens of such structures. If the etching will work, you have a lot of things to play. Again, it needs time a bit. So somebody like needs to take time and to analyze this. It's very interesting. So we could go below Zelda, just below. It's the same. You don't need to. Let's go down. And probably this part doesn't have something more interesting. No. So then zoom out the whole thing, and you can zoom on this maybe quadrant. But I think it is completely do it. Yeah. So this is the same like this all heaters. It's very good that you have a lot of them. Then you can just simply go to the left. Yeah. More. Okay, good. Then you can just simply zoom on these two structures.
Here?
On this
3.
That's 3, okay. Do it 3 and then again on 2. Okay.
It's 2.
2 on the right.
2 on the right. Very good. Okay. Perfect. Again.
Okay.
Just one more zooming probably. Very good. Very good. Yeah. So, what do we have here? Okay. This is actually a principle. You have this 2 deck is big and it goes over the stress part, and this is a recessing part. And this is one ohmic, this is another ohmic. So the current goes like circular, like that. And this is the recess part, and this recess part is staying on the way of the current. So you can, through the 2 deck, this ohmic and this also uses an oscillation, plus 2 deck will conduct the current. And this is like, which we saw before, only much more sensitive, supposed to be to the 2 deck enhancement. It's also this is also a QCM, but with the 2 deck as fully incorporated active element. So you can see this interaction much better, and it could be kind of more selective in this way. And as you have this also metal, which a bit better resonates, and it's also used as a gate if necessary. So yeah. Selda, could you please switch off heaters? Yes, it's only recessing, so it's almost euro part. It's a euro. That will bring money. I need to do 2 here. And be euro. So the metal goes only till here. So recessing part is this. It's very nice, and it will not shortcut 2 deck. And then you have this. This is ohmic and this is ohmic, and then they will oscillate, and this is like recessing part. This is and switch on heater again. Okay. And yeah, this is super simple element. It's a very big 2 deck part. Membrane, and this is the recessing part on the maximum of stress, and this is a heater which can work as a piezoelectric electrodes, as a heater, and then as a gate. So it's kind of all functionality in your structure, which is yeah, a bit simpler. Yeah.
So for this QCM thing,
Yeah.
you need a VNA to find out the resonance frequency, or
Yes, VNA is the best device, which we have. It's already overkill. We have a super fancy device. It's just probe station needed. So, but for such a frequency, maybe probe station is even not needed, because the frequencies for that would be much slower, much lower. So it means for all the normal probe station with the needles stop to work at 1 megahertz. So everything which is below megahertz would work.
Yeah.
So you don't need a probe station. So for this you can just apply only one contact here, one contact here with the needle, and you can even with the spectrum generator. So if the Halliburton possible to take it, you can apply the sinus, and you can increase, and at some point will be a huge jump in phase. It means that you went to a resonance frequency.
Yeah.
You can do it totally the same with VNA single port. You can just split one cable, or like you connect 2 cables ground together, and from one cable you connect signal here, from another port you connect signal here, and you do a scan at the VNA.
Yeah.
And you will see at some point a huge jump. And this is your resonance frequency, and the phase will go through 0 at that point. It means resonance occurred. And then you can adjust the resonance frequency or close to this, and you start separating it with the gas, with the temperature, whatever. And then you will see how this peak will, and it's real time, so it will be like book, 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 scanned like that. If you only really limit to the sector, it will be almost real time. So like 1,000 per second will be scanned of this. And then this peak will just shift. Completely. It's a huge signal because it will completely go to a higher or to a small frequency, and the phase will shift. And it's your sensor response, like a huge amplitude in this. And you can also bias it. So let's say let's bias with DC on top to stress it, and at the same time do a rep. So it will give in the end. It's a microphone. This is even with heater. Then it's a gas sensor, this is a pressure sensor, and everything whatever you want. So it's a universal sensor. So, because it's a multi-parametric thing. So it's very nice to play with that, very nice. Just you need a bit time, and then you are very nicely set. So that's all, this is no SPM mask. So everything, you just repeated everything else just to have a bit more sensors. But if you would have only different sensors, then you don't know. So this is the same, so you have a lot of sensors to kind of repeat And we can repeat this mask like on 3 wafers, 1, 2. I will just only do, for generic, I will do this extended part like you did. So I would replace this crap with this new generics which you are doing, and then you will have this.
I mean, you need only the contact parts.
Yeah, the contact. Like even one thinner, thicker, very thick.
It's a Halliburton small.
Yeah, which is all the same. Yeah, it's just I don't know, and they are too close a bit to each other, so it's a bit difficult to bond to whatever. So
Exactly.
you can just simply replace them and repeat these masks. I would also recommend with these generics maybe to populate all the wafer 1 or 2. So now we have 10 wafers. Yao, I don't know what is his plans. He's supposed already to order new, because the longer he waits, the shittier will be then, because the delivery can be 2 months of new. So and if he has money, he has to order, because if he doesn't order and these wafers are over, that could be. But it's like that. We have 10. 10 is a lot. 10 is a lot. 2 of them are super fancy. Aluminum nitride, so you have to decide
3.
3 aluminum nitride. Ah, yes, 3 aluminum nitride. So aluminum nitride is a big hole. So for super important application, I would think carefully, because aluminum nitride is the best will be. Yeah, the best. Unless they are dead, it also can be, because you never know. You never know how the epigun did, because aluminum nitride is very critical. The terahertz mask, yeah. I will explain you. It's very secret, but I will still explain you. It's the most secret mask. Terahertz mask. Because I was always thinking he wants to detect terahertz. Terahertz is not so easy. You need to edit. Yeah.
But maybe I should open from the other one, because I collect.
I was waiting
Oh, this one.
Yeah.
Can you
Excuse me?
repeat? Because here
Yeah. Ooh,
I-
terahertz mask. Fuck.
I just did collected the one which we have. I mean, you know, not all the layers we has as a physical mask. So the one which has this layer, I only collected in a one design. Shall I find the other one which
No,
all
it's
the
not
layers?
necessary. It's enough. It's enough. I see
Okay.
already. It's enough.
Maybe there is another layer which you wanted to show us.
No, I didn't want. No, this is enough. Can you zoom? Then we see.
Which
because
one?
it's a very small, like this quadrant, for example. First.
Okay.
Okay. No, we have everything. That's all. You see these weird structures. So.
Which one? You want
What
to start
is the
with this one?
best? Yeah, do it. Yeah. Can you zoom in what inside? Can you switch off this one of these elements?
Which one?
One of the two. Switch off one, for example. Okay, very good. It's also green, it's irritating.
Yes.
Change.
You're right.
Yeah, this is okay. Like that is okay. So, what you see here. So, this structure, this is dark a bit. It looks like, you see, it looks like the hole, and then this is here connected, and then it's like that. So actually, this is a Vivaldi antenna. It was calculated by Neil Axelrod. It's a small kind of conic antenna in a way. Normally, it's like it has to be 3-dimensional. Then it's the best. It's so-called conic resonant antenna. So you see this area. So actually, it's working. A sensor doesn't work like that. The radiation has to come from this direction. Yeah. So actually, the chip is like that, and you have to put it vertically, but it's not really important. And then it made this thing. It's just designed such that exactly the dimension of this, it fits for around 1 terahertz of electromagnetic energy, which will resonate here, and the maximum of the field density, it's just, this is structure, it's working actually, you can see it as a lens, kind of, lens for terahertz. a bit shitty lens with very bad quality factor, but still lens. So it's this, when the 1 terahertz is coming, it creates a field density maximum around here, like a pier.
Mhm.
And here is the maximum density between this plus and minus. Because its charges are separated, plus and minus electromagnetic, and here is a place of maximum energy density, electric field density in kilovolt or in volt, whatever. And actually this has to be as small as possible, the gap. But I couldn't do it more like the 4 or 5 micrometers. I was afraid it will just shortcut and structure can throw away. Actually, you have to do it with electronic beam lithography, whatever. The smaller this gap, the higher the field density, yeah? And then normally, and then I extended this one part, because it's one of the potential, to a 2 deck, and you have these 2 deck channels, which running behind. And for example, if you recess here with extremely good working point, this part starts to be super sensitive to the electric field. And the idea was, this is kind of a stupido sensor, like you do terahertz, but you read out with DC, which is possible, because 2 deck pixels already operate like that. This is actually the most biggest sexy part, which attracts every scientist, because how you detect terahertz? Terahertz is so fast, there's no electronic working in terahertz, it's a gap between light and electric. So you cannot detect it really like as a wave, because it's so fast, you will not be able. So they make few types of sensors, resonant and not resonant. This is not resonant sensor, it means that you're creating this field, and it has quasi-DC effect to the conductivity on this channel. So there is something happening on very high frequency with very high fields, and it's influencing this ultra mobile electrodes in the 2 deck, which has also terahertz resonance frequency, by the way, these electrons. And if it's very recessed, it's so sensitive that you can, with this field, influence the electrons. And if you read out conductivity in the constant in DC, this you will have a small change in conductivity. That means it's a kind of an evidence that something very fancy happening at much higher frequency, but it's like an evidential detection, but very stupid. So you don't need any readout, nothing. You just detect and you read out something which comes at much higher frequency. This is like a general basic idea of this sensor. We have a lot of sensors in this mask. And in this case, this is a configuration, so we didn't know which configuration is the best. This antenna is not connected with the source or drain, but it has to be actually, because it's a gate. That's why it's not connected. I didn't know how it was the best will be working. And another sensor has a connection. If you just zoom out, they have a connection because it has to be connected. You can somewhere here.
Where?
Just zoom this big quadrant. Yeah. And some of them can show you.
Where we zoom in?
What is this? Actually, it's this one here. So here is not connected. Oh, there's another quadrant probably connected. So the channels are different. This is the channels is bigger. This is connected here. Yeah. So this is actually structures which is interesting. So you have a lot of gates. Zoom this one sensor. Yeah. So this is, for example, a normal structure. You are connected. So one is connected to the minus, unless you. This is it. We didn't know because we connect, but actually maybe you don't have to because it's very bad, because this potential it's changing, plus and minus are changing very fast. And if you connect, maybe they leak away. I didn't know. That's why we have a lot of not connected, but we just don't know, and we measure them all and see what is working, what is not. And the principle of measurement is very simple. You buy at the company TerraSense, it's called. Is it still recording?
Yes.
Yeah.
Yes.
At the company TerraSense, you buy a terahertz source, which costs around 1,000 euros, not expensive. It's just source. It's like a lamp. And you buy a detector, it's also 10,000 euros, but you don't need really to buy it. And you install over this sensor, so sensor you install directly in the camera, and you just switch on, switch off, switch on, switch off. And with a kitty in a very fancy dark room, you measure where there is a result. And if you see this, you can be sure that you come to a very fancy paper like Nature, because if you are detecting terahertz with a very stupid method, this is one. Second, you don't need, of course, to measure in DC. You can measure in RF as a resonance. That's called the resonance sensor. Quasi-resonance, it's semi-resonant. I will explain you what means resonance. Resonance is a bit more fancy. But it's a semi-resonant. You apply plus and minuses. For example, at 50 megahertz or at 100, it's still high frequency, but by far not so high as a terahertz. 50 megahertz you can buy it a small part from Farnell, cost 10 euros, nothing. But it has some resonance effect with terahertz, a bit beating a bit. And this beating overcome you detect, and its beating is changing when you switch on, switch off, switch on, switch off, still working. This is kind of stuff. And the idea is, what is the idea? So, I wanted to have a passive, detect a passive terahertz radiation. Will never work. Passive, it means you don't have a source. You detect like, so you have a drug or fentanyl or whatever, or some other crap, you put it on the table as a liquid, and you measure with the sensor how they are emitting. That's how he imagined. It will never work, never in the world, never. For that you need to have such a sensitive pixel, because of course terahertz is modulating a bit, yeah? It's what is terahertz? Another word to this, it's a black body radiation. Black body radiation. And it's actually, everything is consists, especially organic things, from complicated molecules. And they have, because they are all not in absolute zero, they have all natural thermal resonances, yeah? And that's actually black body radiation. This is the, normally like Raman, for example, is studying different rotation. And terahertz is longitudinal. This is the same. So Raman is this, so if you have like a polymer chain, it has so many resonances, some micro resonance, whatever, but one which is go along all the chain, every molecule is an oscillation. And of course, when they undergo some covalent bonding or whatever bonding or polymerization, this oscillation changes. And normally what the people do, they even don't hit, there's something, they let them polymerize and they see with a terahertz camera and they see that it's all different, it's like colorimetry, kind of. They interact and then energy goes down, for example, and then they see that the color is changing. But of course, every substance has its own resonance frequency. So this is, and then if you have one camera, they all come to each other and you see like a background, you cannot distinguish. So in order to distinguish something which is very tiny, you need to have a very tiny terahertz camera, which is not possible because it goes below the wavelength a bit. Yeah? So this is like, because the wavelength is like micrometers or whatever. So there is a problem which is not so easy to solve, So they now try to apply, because terahertz is predicted to be the biggest diagnostics tool of the next century, because indeed it's not harmful, it doesn't harm. So, and it can be two ways. So you have a source which has a terahertz, regulation, different frequencies. And at some point you start to interact much better. It depends which is on top, you enhance and it reflects back and you detect this. And you say, it's like a spectrometry. And you say, okay. It's like you want to, with UV, you want to see a fingerprint of humans, you know, on the glass or something, or the criminal detectives, they switch on and then you see, because this polymer, the organic sweat, they start to absorb this UV and fluorescent. And with terahertz it's the same. You have the source, and that's why it's called terahertz-based tomography. It's very fancy diagnostic tool. They shine to you with terahertz short pulses, and they see different reflections in the back. What is going on? And this is actually the idea to use also the sensors. You have like something like is like some drug or something deposited somewhere, and you have this pixel which can energetically detect the response. You shine, it reflected back, and you see difference of this reflection. For example, for some specific frequency, but it's so far from application, it's difficult, and then there's whole institutes working on this. So this was kind of the shot in the clear sky, so the whole program. I want to detect, but it will never work.
And when you compare it to Raman, what would be the advantage for Raman, for example?
The terahertz, it has, because it's longitudinal, and Raman is a smaller, they say terahertz is more selective because you have this unique fingerprints. Okay. If you would, for example,
with Raman, you already do this.
You already for higher energies, and that's why they say for higher energies it overcomes with a lot of electronic things, and it can be not so super like selective. And terahertz is like, if you see this, if you have a methane molecule, for example, and you see what is resonates at different frequency, you see that at like 10 micrometers wavelengths or whatever. It has huge peaks because you just catch this molecule dynamics.
Yeah.
But this is, you always shine to it. This is even not known. If you have, there is such a terahertz glass is not available yet. Terahertz camera not available. Only available, but in a very specific sector like 600 gigahertz or something. This is a military range of whatever. And then that's the thing. So if you have some polymer or something, it may have this terahertz huge. So Steve, the answer is like the quality factor only, because if you see this, for example, the quality factor of this absorption peak is so huge that you just have a bit bigger signal than the Raman. If you have, for example, go, let's say methane, 1 terahertz, 1.1, it's a huge, and 1.15 is already 0.
Okay.
And you have such a huge thing. But hey, you have to get first to this, because it's how you handle it. It's such a high frequency. In Raman, it's red light. Red light you can easily emit. But in terahertz, there is no source, and it's not for by chance no source. It's very dangerous. It would be if such a source is on the nature or exists, because it will exactly correspond to an energy of movement. So the molecules could decay, and this is another one. One of the meanful shittiest weapon of all the time is a terahertz laser, because it goes through everything. And for example, to destroy a living object, like U.S. military and other countries, they work on the terahertz free electron military lasers. So because a lot of terahertz goes just through the objects, like through the walls or whatever, because it's like 1 terahertz goes like through this wall. And then if you have this very strong thing, you just aim to the guy and you shoot, and then he just collapses because it has a huge damage. Like, but then you need, the only problem which is not allowing for them to do this, there is no effective mechanism how to excite terahertz. So amplitude which is coming is so tiny. So that's why they use it as a lamp, boom, like a military. They want to see a tank behind the tree, so they switch on the lamp, tank is staying, tree is invisible. This is so-called terahertz, like Apache longbow has its own as this kind of this bow. This is actually terahertz cameras, but it's a sub-terahertz, not really terahertz. Terahertz camera is not yet available. There is only one very good source of terahertz called free electron laser, yeah, or undulator. It means electrons, and undulator has unlimited. So it's a dream of all physicians. So actually, this is a superconductive such a 6. It's like a magnet like that, with potentials. There's like potentials plus, minus, plus, and electrons are flying. And then with some specific frequency, it starts to undergo such oscillation, the electron. And because electron is in vacuum, and because it's very small, you can naturally, by combining these phases, have a very high frequency of oscillations. And because it's such a high frequency, you generate electromagnetic energy with this frequency. And this can be from 0.1 terahertz to 20 terahertz. So you can generate with this free electron laser because of the things. And in Germany, they built this DXE. This project. It's a free electron-based X-ray laser. This is the hope of the whole physics. So what it means? They create such a massive radiation that you can. Then they want to see how the chemical reactions happen in the molecule level very fast. They want to image the reaction, which happens in 10 seconds only. And this is in Hamburg. It's like the France participating, Russia, Germany, Japan, US. It's a huge free electron undulator-based X-ray laser. So electrons move so fast that it reaches the X-ray frequency. This is terahertz, one of the crap. It starts already from terahertz, but it's so fast moving that the X-ray of super high intensity is producing. Super high. You can burn with X-ray. You can burn a metal. But it means that if you focus on some very specific like molecules which undergo some reactions, and you focus this for a very short of time, you have an image of interactions between the molecules. And this image is real-time generated. And you know, for example, how some of the reactions, they happen in femtoseconds and people don't know why. And they study with these lasers actually, yeah. You can zoom out a little bit and then we can go to the structures. Yeah. This is a kind of a terahertz project. What I actually want with this project, yeah? It's insane, I will tell you. He thinks that there was one scientist called Yuri Feldman. He said that from the sweat glands we're emitting terahertz. This kind of total bullshit. So the thing is that I want just from the hand emission identify a person. That's a full body identification based on the terahertz. So not only he don't want to detect, he want to identify a person. This is like 20 times more difficult as to detect terahertz. It's such a bullshit. I mean, because we're all emitting a lot of terahertz and things, which is also people expect from the terahertz diagnostics. They believe that in the body there are so many, especially with the immune system, there are so many, like with the X-ray lasers, they want to understand how the things are in the chemical crystals happening. Yeah. With terahertz, they want to understand if you do a pulse to you, like boom, they think like the smell, brain, or whatever, a lot of cells, and during the cell splitting, when the cells differentiate, they believe there is a lot of interactions on the terahertz level. And they believe that, for example, if you drink something or you eat something shitty, it's immediately, the whole reaction is already spreading of the whole body, like, or interactions or whatever, which it's already pre-programmable, visible. It's like freaky studies, like also immune studies or whatever. The kind of, it's not good for you and they want to see what is good, what is not, so they want to have an image of an interactions within your body, like activation channels if you do something, but for very short time. And this is very difficult. Now they build such a huge things, one person lays and they do this terahertz image, like femtosecond, the terahertz tomography image is like, they activate but only with a red light. With free electron terahertz laser on human is not yet spread because it's not yet completely understood whether it's very harmful or not. Should be not harmful, but it's not yet completely understood. So this is 1,000 type of sensors. You can go below, there's like sensors which are even based on transistors. Here.
Where? Sorry, pardon. Say again.
Here.
This one.
Yeah. So it's this is a transistors, and you have a terahertz antenna, and you can just simply with VNA you can shine with your terahertz source like from here, and you see whether VNA peak has a shift because it's already much higher now. Now VNA goes to like few gigahertz. It's very interesting. I mean, maybe it's in this frequency. So this is non-resonant sensor. What's just terahertz resonant sensor? Terahertz resonant sensor is like that. So this is non-resonant. Non-resonant. It means that you have a channel. This is like non-resonant. It's a kind of stupido sensor. Kind of. You have this. You have, for example, something which is like volumetrically absorbing terahertz. And you have two-deck channel, and this is like recessed part, very, very sensitive. And you shine, and your influence on the, it will do a flicker. It will do a flicker to the camera. Yeah, it's yeah. Okay. It's visible, everything.
Yeah, make it visible.
Yeah, no, it will, yeah, it's a big, you will see. So it will be visible. So this is a terahertz coming, yeah, the quantum. And then this bolometer material, that's what the cellular has to fabricate. This is one of the most important projects for So this bolometer material, which can be graphene, by the way. We can order graphene exfoliate with my gun without any Israeli institute. I mean, we don't need an Israeli institute for that. I mean, come on. You can order now graphene on whatever copper on platinum, and you can exfoliate, and you have, for example, your sensor, and you put nice graphene foil, poof, and it's actually very interesting. Yeah? You have to be only careful not to shortcut with graphene with conductive. Yeah? Yeah. But if you somehow manage, you can just remove graphene from there or something. I don't know. Graphene, for example, why I say graphene, it's interacting with the terahertz because it's an absolute material kind of, and it's immediately transferring the electromagnetic energy to a graphene oscillation, yeah? Because it's 2D. But there are a lot of materials which are terahertz sensitive. You can put even on the argon. You can order polymetric material which needs to be cooled, but we don't need to cool. It's funny. You put an argon as a lens, or you have an argon sensor, like argon sensor from the side, and you put a Teflon lens. Teflon is focusing terahertz. You can let Eric fabricate this because they wanted to buy this Teflon lens for 3,000 euro. I mean, crazy. Eric can do it a bit cheaper. So you can order a bulk Teflon, and he just CNCs one lens from that. Very nice blunt convex thing, and then it will really focus terahertz here on the sensor. Not so good because these lenses are not so good, but it will. And why? Because you have this kind of the Teflon is also these chains, and for this specific terahertz they just interact, and it's like in the optic. And you do Kitley here, and the Kitley is doing change on conductivity. So this people already did. You have a lot of nature papers. You can see experiments. They put metallic key, cover it with a book, and with a gun they just drove like that, and the key was built. It was very fancy paper actually, and they put also cross under the book. Book was small, cross was from metal, and they were just scanning with a normal gun sensor in DC mode. And there is some modulation. It was not cool even, and in the end they see something like very bad picture of something like when they study the amplitude, similar like cross. And then it's supposed to be not electrostatic, there was a lot of things. So it's a bit fantastic. So you can do this, it's called non-resonance. So you, in a very high frequency, you put, it interacts and your energy changes, and the super fancy recessed part, even non-recessed detecting operated terahertz, recessed supposed to be detected outcome better. And then you have a conductivity change, whoop, up or down. We did with Chen in Vienna, and we saw something like that. We drove with a lot of sensors to Vienna. They have a lot of terahertz sources. It's called backwards oscillator. You can also buy it if you're lucky, because it's actually from military based. It's such a black box with a magnetic field where the electrons also rotating. And you can adjust with the magnetic field the terahertz. Not all spectra, but like say from 500 gigahertz to 1 terahertz you can do. It's such a black box, and it's not focused, but it doesn't matter. You put sensor on top of it. So the Technical University of Vienna, they have a lot of dozens of these backwards oscillators they got from Russia, from some military things, it's kind of connection, but they are all staying like up to a ceiling. They have in Germany, I don't know, I think America forbid to sell this. We try to order and they say backwards oscillator not so easy. So, because they think why you would need this and such a stuff. Maybe if you clarify that it's for medical purposes, maybe they will sell. So that's non resonance sensor. Every electron has its frequency, because there are electrons, they interact each other and to each other, and they actually hate each other. They're both negative. They want to go away, but they are all moving in one direction, pressed to two deck. There is no, so they cannot escape. They kind of interact, and this interaction creates a quasi-particle called plasmon. The whole quality starts to oscillate. One electron just did such a movement, and then wave, and this wave is called plasmon wave. It's a movement, collective movement of electron in the two deck, and this plasmon has dynamic in terahertz range, because it's electrons, they're like in one, like free electron laser, only put it to two. Much more shitty, of course, than this. And it also moves, electrons are moving like that, here in two directions. And this is plasmonic movement. When the electrons are going like this, is a potential difference. This is very simple. The resonance sensor by itself, it has no limit. People are still developing it, and we're working to Ferdinand Braun Institute, where we're testing. The whole institute is working for terahertz resonance sensor. The whole institute. So this is, for example, this is a potential difference of source drain in the two deck. So you have a potential difference, and the electrons here, they change the energy, because one is high energy, and that's why they flow. And they have like plasmons, and then people, they on this level, they install like bimetal gates, such a thing that you have kind of staircase instead of rolling stuff. So you have staircases like of this energy levels. It made by metal. So if the channel they put like metal gates, but depends on the potential differences. It has to be different distances. So they modulate, they simulate how you have to put these things. And the idea is, if you accumulate, this is a barrier to some certain level, you just electron jump, and when you apply potential difference, this potential, the staircase changes. This starts to be lower, and then suddenly you have a cascade of movement of electron. It went into the resonance. If you shine terahertz, and if you couple this plasmon, and there are plasmons of electrons, they are connected here, and then you start to everything has to be in the resonance, and then it affects, but it's always at higher frequency, because if you see a DC, these effects will be not visible, but at higher frequency, the resonance effect happens less with the terahertz. They happen, for example, with 10 gigahertz, because the plasmons happens in terahertz, but this jumping based on this resonance happens at lower frequency. And they use these sensors, like they look like a tie antenna, such as things connected with some RF, you can see it. And they have resonance frequency at this frequency, and you shine terahertz, change RF parameter of this antenna. So this is called resonance sensors. It's this is, you have the structures, and then the electrons jump, and then you have this resonance frequencies, and you properly read it out, and you have like a peak change to this, for example. And this is a big detection, I must say. And this is the resonance structure. We don't have knowledge for that. So there are a lot of papers, okay, so we can do it, but the problem, there are structures below 100 nanometer. Because you need to have a really energy barrier, very small, otherwise you will not resonate. 100 nanometer E-beam means. E-beam means very complicated. So that's why we focus on this kind of stupido sensors, like non-resonance sensors, like that. And using field concentrator, instead of this lens, divide the antenna. And we were hoping for the best, like that. This is also with a ref. It's a stupido sensor, it's not resonance, but with a ref to see like a beating maybe effect. And you can zoom out, we have the whole wafer of this sensors. So we fabricate like, I think 2 wafers maybe, I don't know. Maybe they're not all diced. Yeah. Can you zoom maybe here? There's another system. There's another idea. That's why I wasn't really hatching. So I was asking what I was hatching in UV. This is calculated by Noel Axelrod. This is a photonic crystal in the gun etched. And normally for the terahertz, that's calculated for around 500 gigahertz. So if you shine with a thing, it works as a photonic crystal based on the gun dielectric constant, because it has to base on the gun dielectric. And then it makes some reflection or negative things. So it activates all this energy. And the idea, if you have this in the crystal incorporated, so to the cascade, such electrons, and you have this working point, you can see in the channel this energetic reflection on the stupido way, non-resonant way, of this terahertz influence on the photonic crystal. So actually it's a readout from photonic crystal. And we have 1,000 structures here, all different, to see what will be the best. You have a lot of photonic structures with the recessing. So this is all photonic structures. We have different things. Maybe they will somehow work, maybe not. This is just, it's a question. It has to be first fabricated, properly mounted. We have already fabricated the laying in the cupboard in the lab, such a big carton box, and also a lot of on the clean room. You can also time test them. So it's yeah. And what is this for unique thing? Oh, this is a very new part. Yeah, they are all the same kind of. This is the so-called Aharonov boom structure, what the people get Nobel Prize. This is the negative breaking index structures. So if you will shine from here, it will not break like an sim, so it will reflect below in this direction. So it will come here, it will come out here, so it will completely reverse light. Why? Because this metallic, sometimes they are connected, sometimes they are not connected. This is a module of a molecule, according to them, because the field is electric and magnetic fields. And in this case, they catched against each other. So the magnetic field and with electric field create a current which coherently couples with electric field, and it turns the photon. So it's kind of, what is this? It's nothing else as a metastructure, so-called metastructure, which is kind of increasing, like normally the atoms do this, but it's like in the bigger way, depends of course on the wavelengths. This distance has to be calculated properly. On the terahertz, normally it works for light. In terahertz, it could be really bigger. So this is for 300 gigahertz calculated from the book, Aharonov Bohm structure. And then this is like recessed areas, and this is ohmic contacts, plus minus, and it's not connected. And then they focus field here. This is also the ideal equivalent. Here it's the maximum field densities. And if you have this recessing area and they're connected with the two deckers again, you hope that when you shine this, you have a modulation of the current a bit, which we saw. In Vienna, we saw this modulation with this stuff. That's all. More I cannot tell you about this because I don't know myself. This is absolutely very experimental, and very secret. It's very secret.
Yeah.
Yeah, no, he understands. That's all. And then you can move on. There are some small, you can see, small, very small, 600 gigahertz, I think. This 500 is even smaller, 600 are calculated to distances. Some of them connected, some not. So all variants to see what will work the best. You go combinatorically from one to another because we don't know what's exactly involved. So that's a terahertz masks. Yeah. Which is, by the way, so complicated that for that you need to open an institute because this is things which you cannot like touch like so easily. So I need to theory. Actually, you need to simulate this. It's a ohmic Aharonov Bohm. So another principle. Ohmic pixel. It's a single pixel, Aharonov Bohm pixel. It's a shortcut diet Aharonov Bohm. With the shortcut splittage, you split out this. You array. Yeah. That's all. So, but I think this mask is a bit. It's so specific. So. You will not have time to touch it. I have so many other masks. I mean, this is just a bit time wasting. It will be. Yeah. Economic point. Yeah. And here. And it's all photons resonate, and then you detect. You measure what's going on.
The small points means it's the recessive.
Recessed. It's recessed. Yeah. I did, I think, one wafer only, and I think only silicon carbide. I recessed, if I remember. And then with that.
I will check.
Yeah. In Julich I did.
Yes.
Yeah. That's all.